Is it out here? The story opens with one occasion. Solving it numerically poses no difficulty. Solving it in logarithmic time and linear memory is another matter entirely. And chasing that goal drew me into some genuinely fascinating mathematics. This video presents my original paper together with its reference implementation, which I worked on for the past 6 years, mostly due to the lack of theoretical knowledge on my part. But let me start here right still. In 2011, Paul Borque published random specifying on the plane, and not in statistical geometry. This is actually a great read. I encourage you to pause here and check it out in full. It introduced an iterative algorithm for tidying n-dimensional space with non-overlapping shapes. The visuals were indeed stunning, the algorithm behind it far less so. Here is a median circle fractal. The gated generation time was 14.7 hours. Nor did the method grant much control over the resulting distribution. Can you do better? The flaw lies entirely in the random sampling. As more and more shapes are added, there is a vanishingly small chance of finding an empty spot. In the limit, it takes an unbounded amount of iterations to insert one more shape. In this visual, I see several random symbols ending up inside some shape, therefore rejected. Finally, one is found to be outside. It is quite close to the edge too, but we have no choice here. A new circle will be added, centered as the current sample, even though a more optional solution is clearly available. This is what I meant by the lack of control over the distribution. Consider a different approach. Represent every shape by a signed distance function. For a binary set S, its signed distance function returns distance to the boundary. Negative inside the Z, positive outside. Solve properties will carry us too. The gradient has unit magnitude almost everywhere, and the function is one Lipschitz. Its value cannot change faster than you move. Now fold all the primitive SDFs into a single compound field by taking their pointwise minimum. We say that G of V is the minimum over all primitives n of SDF n of V. The minimum of one Lipschitz functions is itself one Lipschitz, so G inherits the very same regularity. Because an SDF's gradient always points away from its surface, he can build an iterative algorithm to travel along that gradient. Naturally, finding a local maximum outside of any shape, precisely the argmax of equation 1. This algorithm has a name, gradient ascent. Problem solved? Not quite. Evaluating that pointwise minimum over n primitives costs O(n). Leading the plane with n shapes therefore costs O of n squared. We have merely traded one bottleneck for another of the same order. Consider a bitmap of size n by n and rasterize the field onto it. One single precision sample per pixel. Lay the pixels out along that order curve, so the spatially close samples stay close in memory. Then scan them one by one for the global maximum. Is it hold up? Good enough for a toy model. I look up is no hole of fun in principle, but increasing precision causes both quadratic time and quadratic memory. The 4036 by 4026 grid shown here already serves an average discretization here of 2 to the 10 minus 4, while consuming 64 megabytes of memory. One can come up with more optimizations, split it in chunks, but this will merely change the constant before a big hole at the end. The baby adaptively sampled distance fields by Priskin et al. Proposes reducing memory by approximating the field within each node of a KD3. It gives little guidance for a practical implementation beyond fitting a polynomial per node. Precision will then be limited by chairs and polynomial degree, as well as the quality of the regression algorithm. Current work takes a different route. Each node, a bucket, stores the primitives, function pointers themselves. The purpose of buckets is spatial locality of relevance. Far from a shape, that shape never wins the minimum, so there is no reason to keep it here. Each leaf retains only the handful of primitives, sufficient to fully define the field inside it. To sample G at a point, ascend to its leaf and minimize over that one short bucket. G of B is a minimum over the primitives F in the bucket of the leaf containing V. The cost is order depth plus beta, the bucket size. On a balanced tree, the depth is logarithmic and the bucket size beta stays constant. So Gary runs in hollow n, never once touching the millions of distant primitives. The next section develops the algebraic formalism in its entirety, on which the crucial optimizations rely. If you rather see the final results instead, jump to 21-minute mark. The sadness of everything that follows rests on Lipschitz continuity. A function f is very Lipschitz when the absolute value of f of a minus f of b set most L times the distance from a to b for all a and b. Geometrically, the graph is confined to a cone of slope a. The single sampled gather with the constant being the function across an entire neighborhood. True SDFs are 1 Lipschitz. Estimators simply declare a larger L. Next, assume you do not yet know the definition of Lipschitz continuity we just discussed. A big task for you. Given one-dimensional interval and two functions, f and g, how would you prove that f greater or equal g on the entire interval? To clarify, you do not yet know anything about the functions at this moment either, and the only operations you are permitted is to sample a value of the functions, one place at a time. Perhaps you can sample it on regular intervals, stopping once you found the spot where f is less than g. But what if other samples were positive, but there was a sharp spike in mid-figure samples? Your strategy will yield a false positive, leading to some nasty issues down the line. And besides, in the degrees, a regular grid test will take all of unscared in terms of resolution. You can only increase it so far. Another idea? Perhaps come up with some fancy entire point method optimizer. Think on your own. Here is my solution. Since f minus g is a f plus LG gives for every V in the terminal F minus G at V is accused its value at the center C minus the sum of the Gibbs constants LF and LG times h of R, the half diagonal of R, set inequality powers a branch and bound over rectangles. Let delta be f minus g at the center. If delta is negative, return false. A witness where f is below g exists. If delta is at least the Lipschitz sum times the half diagonal, discard R. F dominates G on all of it. If we hit the depth budget K, return false and observatory. Otherwise, split R into 4 quadrants and recurse. If the stack empties, return true. The test is sound. It transfers true only when f is greater or equal than g truly holds, and is otherwise merely conservative. Its cost adapts. Well-separated fields resolve at the root, while a genuine fitness is found by discant rather than by any fixed grid. In certain primitive f, over the domain visits every overlapping cliff independently, in parallel, resolving each draw that predicate. If f is at least the bucket field on the reef, allows nothing, no hope. If the bucket field is everywhere is at least f, then f dominates. Replace the bucket with f alone. If we had the maximum depth d, as the bucket is under capacity delta, sorry beta, append f. Otherwise subdue it. Give each child the combined set, pruned. Prune of b over r keeps exactly those primitives f I that are not everywhere dominated by the minimum of the others. That is, that still define the field somewhere in the R. Each comparison runs through that same sound predicate. The primitive is discarded only when probably redundant. The start field is never corrupted. Reading can err only towards keeping. Notation remains. Where can an insertion actually alter the field? A shape based at a maximum x0 fits inside the free ball of radius t equals g of x0. So f of v is greater or equal than norm of e minus x0 minus t. And the field can shift only within g star, the set of points v where the current field g of v exceeds the distance from v to x0 minus t. For a global maximum, g is less than d everywhere, so d star sits inside the free ball of radius 2d. Its minimal abscissa-aligned cover is the square of set 4d, and the constant 4 is optimal, attained by 2 tangent paths. Historically, he got left at a 4 times root of 2 bound by trial and error, like in any theoretical basis. In the end, it was sound, but twice oversized. For a local maximum, no square of side proportional to t is sound at all. 3 contact points with gaps under 180 degrees leave an escape ray along which the field stays above f. And so we say that G star is inexpressible in units of t. Instead of a fixed rectangle, The function inserted maximum prints the tree value itself, discarding a sub-tree R once. G hat at the center of R plus the bucket constant LP times the health diagonal that was the distance from R to x0 minus t. Here G hat is a not's own packed field, except at the reef, and at an internal mode a pre-subdivision snapshot, which takes a valid upper bound, because insertions only ever pass the field down. Lastly, I'd like to briefly mention cat-tree implementation itself. Rather than dynamically allocated each node in heap, the tree lives in a flat arena, even not in one contiguous array. A node names its 4 children by the index of the first. Since the 4 sit contiguously, siblings stay cage adjacent. The whole structure takes a single allocation, and, being purely index-based, admits a lock-free parallel traversal. The child link is an option of non-zero SRC2. The niche fits it exactly into 4 bytes. The whole node is exactly 64 bytes on cache line, with non-variant marking leaf. Optimizing memory footprint further is definitely possible, but not in my current scope. Unlike the bitmap approach, newly obtained representation is lossless, offering a 10 to 100 times memory reduction, and is continuously differentiable, making it possible to reintroduce an iterative optimizer. For practical purposes, I use an adaptive gradient extent, which makes GGIDF a local maximum method. A trial step flank H is adapted only if it raises a field, so the iterate climbs monotonically. The step lengthens when a move succeeds and contracts when it fails. Watch the plain rule run first, its direction taken straight from the gradient. The maximum of a distance field lie on the medial axis, where G is not differentiable, meaning the ridge. The raw gradient presides on every trail. The path zigzags across the crease. Rejected steps prone through the evaluation budget, and the iterate stalls short of the apex. The queue costs a single vector. Fold the last accepted direction into the next. GK is a normalized sum of the union gradient of G at PK, and the previous direction DK minus 1. The cross-ridge components no cancel. On the second run, travel straight along the ridge, settling onto the kink. The complete update formula is follow. PK plus 1 is PK plus HK times DK if G improves, else PK unchanged. And H is multiplied by the graph factor on acceptance, or the decay factor on rejection. This beats my original fixed exponential decay schedule on 2 counts. That schedule burns a constant number of steps regardless of convergence and cannot refine a kink, whereas an adaptive rule stops the moment the steps falls below tolerance, and bisects onto the exact maximum. On my benchmark, it creates the maximum up to 3 orders of magnitude more precisely in fewer field variations. An Evangeline gradient, a flat region such as the clamped idea of an estimator, terminates the scan immediately, rather than wasting the full iteration budget. Compare them once more. parallelism is delicate. An entire batch of maxima is located against a single snapshot of the field. Yet every insertion mutates it. Their guns are read only, and so embarrassing the parallel. The hazard lies in permitting their results, since some maxima from one batch might place overlapping shapes. The batch is therefore deduplicated. A maximum survives only if its prequel is disjoined from everyone already kept. Accept Mj if and only if the distance from Mi to Mj exceeds Di plus Dj for every already accepted maximum I. Disjoint fables guarantee the shapes cannot overlap, whatever the insertion order. So the batch commits without a look, and the next batch reads the field afresh. The three update follow the same schedule. A read-only parallel pass decides every leaf, then a brief sequential pass applies the structural edits. So, how long does it take to make a median circle fractal? Forty-nine seconds on a 4-claw machine. The resulting IDF3 contains 159 gate nuts, totaling 59 megabytes. So far, we've only seen simple circle shapes. Let's try something much more funky. Implement a manual distance estimator and fit 20k instances of it. Can the current GTIDF implementation handle it in reasonable time, if at all? The manual estimator is not a true SDF. Its gradient is unbounded near the boundary elements, so the one chipshot bound no longer applies, and moreover, the interior is clamped to 0 altogether. I therefore declare a larger usage constant, which keeps every soundness guarantee intact, while mere reluctance are brewing. The constant is stated once on the type and propagates through every rotated, scaled, translated copy automatically. Seven seconds. 3.4 megabytes, 0 errors. Computations and future work. First, today, the implementation covers only the 2D plane. 2. Extending it to n dimensions proved to be straightforward. Nothing in the CLAD 3 says DFs or the optimizer assumes a particular dimensionality. Second, only insertion is supported for now. No deletion or movement. Third, basic driving is included, but I recommend a third-party library. The implementation was intended to be compatible with any driving API out of the box. Fourth, a GPU port is feasible at following assessment. The device should serve as a read-only field oracle, never the mutator. The float CAD3 arena uploads as is, and the surprisingly parallel sense of finiteness parallel are the natural kernel, and every insertion staying on the sound CPU patch. The price is generality. Packets store arbitrary function pointers which your GPU cannot process. So primitives must be reified into a fixed shape higher. Baked distance fields covering everything exotic. The theoretical gains are lopsided. 10 to 100 times throughput on the ascent phase itself. It perhaps 3 to 10 times end-to-end by Amdahl's law, while the structural updates remain on the CPU. Nor can the batch simply grow with the hardware. And batch survivors are kept by how many disjoint variables the current field admits. So the useful batch size scales with the field state, not with the car count. This is all. I hope you learned something new. Excited to see what kind of art he will make. Feel free to share. The rest of the video contains varied visuals from my time working on the project. Enjoy! Goodbye!